Modern neural networks function as geometric engines. Every data input and synaptic weight exists as a vector with geometric coordinates in a high-dimensional space, violently sliced by a flat decision boundary. The foundational operation of a single neuron, calculating the net input, is a geometric interaction. It measures how an input signal aligns with the neuron's parameters. In the late 1950s, Frank Rosenblatt's early perceptrons were physical, hardwired systems. The connections between neurons were actual cables, creating a tangled hardware architecture designed to route electrical signals. These physical wires are now represented as software matrices, but the math remains identical. Each of those connections represents a vector spanning an n-dimensional space. Evaluation of these connections happens through the inner product, W transpose P plus a bias B. This calculation determines the geometric projection of an input signal onto a specific weight vector. Training a neural network involves manipulating this specific geometric projection until the boundary separates the data classes correctly. To optimize learning rules and scale network capacity, we must master the geometry of signal and weight vector spaces. A formal vector space, denoted as Rn, operates under strict axioms. The most critical are closure under addition and scalar multiplication. If you add two vectors in the space, or scale one by a constant, the resulting vector remains within that same space. This gives rise to subspaces. An infinite plane extending through the origin of R3 forms a valid subspace because it satisfies closure. A bounded box floating in that same space does not. Inside a valid space, input vector P and weight vector W extend from the origin, separated by angle theta. Their inner product measures alignment, requiring a perpendicular drop from P onto W. This projection's length is its norm, the square root of its inner product. This geometry dictates behavior in competitive neural architectures like the Hamming network, which uses prototype vectors to classify inputs. The inner product reaches its maximum value when the angle between the input pattern and the weight prototype is 0. They point in the same direction. In a competitive layer, the neuron with the highest inner product, the closest alignment, suppresses its neighbors and wins the competition, firing to recognize the target pattern. The inner product is the physical mechanism the neuron relies on to measure similarity and execute pattern recognition. Moving from a single neuron to an entire network layer introduces a structural risk. If the weight vectors assigned to different neurons are correlated, the network processes redundant information. This creates linear dependence. If one weight vector is a linear combination of other vectors in the network, it occupies no new dimensional territory. Eliminating redundancy leaves a basis, a set of independent vectors that span the target space without overlap. In a two-dimensional visualization, independence is obvious. In a high-dimensional weight matrix containing thousands of parameters, we need a mathematical method to prove independence. The definitive audit for this is the Gram matrix. It evaluates every vector pair in the layer, with each cell populated by the inner products of those vectors. By definition, the resulting Gram matrix is symmetric across its diagonal and positive semi-definite. We evaluate the independence of the layer by calculating the determinant of the Gram matrix. If the determinant is exactly 0, the vectors are dependent. The network contains redundant, overlapping parameters. A strictly positive determinant guarantees linear independence across the entire parameter space. The Gram matrix acts as a diagnostic tool. Mathematically verifying the network architecture isn't wasting computational power extracting the same feature multiple times. Linear independence guarantees no direct redundancy, but it is insufficient for maximum computational efficiency. Vectors can be independent, yet still highly correlated. The optimal state is orthogonality. This requires that the inner product of two vectors evaluates to exactly 0, which positions them at a 90-degree angle. Orthogonal weights ensure 0 overlap in feature detection. Each neuron learns a distinct, independent pattern. To achieve this, we must transform a raw, correlated dataset into an orthogonal basis. The mathematical engine for this transformation is the Gram-Schmidt orthogonalization process. Step 1 anchors the first raw vector, x1, locking it as the foundational basis vector, u1. Step 2 addresses X2, calculating its projection onto the U1 axis to determine overlap. Subtracting this projection shadow eliminates correlation, leaving the perpendicular component as the orthogonal vector U2. This subtraction logic loops across all dimensions, sequentially removing correlated components against every previously established vector. The final step normalizes these orthogonal vectors by dividing them by their lengths. This reduces their magnitude to exactly 1, establishing an orthonormal basis. The Gram-Schmidt process is an engineering mechanism that purifies weight spaces, ensuring that the network extracts independent features. Data structures or architectural constraints sometimes require the network to operate within non-orthogonal, skewed bases. In a skewed space, the standard inner product is insufficient. A standard perpendicular projection fails to map onto the coordinates of the skewed grid, generating an inaccurate expansion for the signal. To decode coordinates in skewed space, the network relies on reciprocal basis vectors. Each reciprocal vector's inner product with its primary basis equals exactly 1, and 0 with all others. Evaluating the signal against the reciprocal vector accurately maps coordinates along the skewed axis. Reciprocal bases allow networks to extract correct coordinate expansions, even when the operational environment is skewed. Linear algebra provides the framework for neural engineering. The inner product calculates the spatial projection of data, establishing the decision boundary that separates input classes. The Gram matrix audits the architecture, identifying redundancies in the parameters. And the Gram-Schmidt process engineers the independence of those features, forcing the network to capture distinct patterns. Without these geometric guarantees, learning algorithms consume computational resources processing redundant features, failing to utilize the network's full capacity. When you visualize a decision boundary slicing through a data cluster, you are observing the output of an orthogonal, orthonormal architecture performing its mathematical function. Structuring the signal and weight vector space is the prerequisite for designing, training, and deploying robust neural architectures.